let's define attractors to morph this surface. Let's say that I would like to create an extension of the ribs and that people will use it as a sitting element in this entrance hall. So for that, I will create a curve that is 45 centimeter above the ground, that it will pull this surface towards that curve. I want the sitting element as wide the distance between these points, because maybe people would like to sit on this this extension from the wall just by waiting for the elevator or something else, waiting for someone to come downstairs, upstairs, etc. So let's see. And yeah, let's create a curve. So I create more points because I don't want the sitting element goes all the way to this wall, but I would like to create it in a rather limited area. And so that's why I define this midpoint of the wall, and then I would like to create the sitting element halfway. Let's create another point so that we can get this boundary out. Just some helping lines in Rhino. And then the point, I write P and then yeah. So let's define a nice curve, a Bezier span, just by right-clicking on the node A. I'll just directly set points in here. One point. So the curve will be something like this, depending on the tangents. It will be the tangent of this position. X vector. Yeah, and similarly this place. So yeah, we are not really seeing any difference because we did not really give any values in these vectors, but let's change a bit. Instead of this, let's do it like that, and minus, and then this time I will, yeah, it doesn't really matter probably. If you want to articulate this curve more, you can basically multiply it with, let's say, 1.5. Something like this, or just basically giving more. So whichever you want. This too much, Let's keep it something like this. And then we need to move it a bit. Move the curve. And then we would like to move along the z-axis, so that unit z. I need to be more close or more zoomed in. So yes, let's write it like this. Yeah, so basically we position the curve that we would like to pull the surface towards this curve. Okay, let's name this group of components by grouping them. So just group them, then setting position at attractor points, and then add to the group. We need to deconstruct this surface, or just divide the surface, to get its points, its normal vectors, and its parameters. So then we can move or change or do whichever geometric operation we need to do, and then get this transformed parameters and points and vectors and transform it into the new surface, which is the extended or pulled surface in this case. So let's plug this into here. I will be a bit closer. So you can change, so what it gives to us a set of points that you can easily see on our Rhino screen, and a list of normals, that normals onto this points, normal vectors, and then the parameters, that is the coordinates at the division points. And yes, so what we will do, we would like to pull these points towards, not all the points, so we would like to pull some of these points towards the curve that we created over here. But the thing is that first we need to find which points that should be pulled, because we would like to specify a position. We won't deform the whole surface, but we would like to deform a specific position. And logically, it would be the closest points to that curve. And in order to calculate the closest points, we have a specific component in Grasshopper called pretty straightforward closest points. Then it takes the points to search from and the cloud of points to search. And now we can define the number of closest points to find that we would like to search from this points, then this will go over here. So this is the reference geometry, reference points basically. But we don't have points, we have a curve instead of points. So we need to define points based on this curve. And for that, let's say divide curve, and this is our curve. We have a list of points that are based on this curve geometry, and now we can define how many number of points we want to have. So by default this component gets 10, but we can change that more. We can define more, so then it's more dense. So let's make it 20, and then in this case we don't have many things to be calculated, but still we have the impression of the curve. It's not too less, so then we lost sort of the impression. We want to be as precise as we can be, but we don't want to be we don't want to have the program or the code be too heavy to calculate. So let's make it 20. It's a good compensation. Okay, now over here we have the points, the reference points, let's say. Yeah. And then you see that there are already some points, but then we see that this is too much. Why this is happening? It's because we have lists in here. This is why it's happening. So usually, what should we expect? We should expect only this part of the points, right? Not the rest. Because our reference geometry stands in here, not there. So we need to give more specifications. So you see that here that we have lists and lists. Let's see what is there. Not this compound, list item. The first item is this. And then let's look at the second item in the list. It will be here. So the third item, so it's here. And then how many written in default? 3. So basically this component sees that I have, which is not true in terms of points, but which is true in terms of the list of points. So basically we have these rows listed as a single item. That's why we're reading the closest points, not as closest points, but as the lists of closest points. So if we define this as like 1, you would see that this row is the closest. Yeah, the third row. But this is not what we want, because we want to select each points individually. That is for we need to change the data structure over here in the point, because it's given as a tree data structure, basically lists in lists, but then we would like to flatten that. What flatten means, simplify this list panel. Let's see again. Simplify this list into single items of points. Currently, that we have lists in a list. So we would like to reach each item individually. And so in order to change the data structure, you can write flatten the tree. So you find this component over here, or you go to sets tab and then tree. This is the data structure components that you can do many things with it. So so in this case it's flatten here. You can also select from there. You can as well by right clicking on here this node, output node, and then you can choose to flatten. So you will see that the list will become 1, and now we can reach each item individually in this list. But you can also use the component. Why we need to use this component? Or we can just do this. But sometimes maybe you would like to use the tree structure as well, and then you want to keep your source as a tree data structure of these points, but then you would like to just use the flatten list for some reason, and then you can still keep the source and then use this lists in a list for a different reason. I drag this and then created my flattened list, which is a simple list, and then you can see the differences. And then once you use the list component, for instance, just write list item and then take it from here, and then let's see the first item in the list, and it's just a point, not these rows anymore. And it's not the case in here, I think, in divide. It's simply a list of points. We can save the data structure over here by plugging this point list of output in a panel, and then you see that there's only one single list. Okay, so now we have the right data structure. We should plug this in here, and then sorry, then this should be in this cloud, and then this should be the reference points. So this exactly what we want. We don't want to have just a single row. We can define this number as well. Let's put it 3, 2, and then this one. Yeah, let's keep it like this. We defined the closest points, but still we did not pull. So pull point, this is the pulling geometry. It could be the points, it could be the curve itself, or it could be, if you want to pull more points as much as we can define a surface over here between the curves. Let's say offset, or I think move would be better. Move this one, and then just move let's say 10 above or set number 5. And then I need to do it again. 5. Yes. So this basically, and edge surface, identify this. I think it's enough. So you can basically use this geometry as well over here instead of this points or the curve, and you like to pull these ones, and yeah, basically you see that it's pulled. If you use points, it will be like this, and if we use the surface, basically that we will pull more, we can define more. Just 3. So we start from here, remove. Yeah. Okay. And then since that we pulled these points, and now we can actually move the curve over here in order to pull more. Move. So a lot of move functions around here. And then I would like to move yeah, on the x-axis, so x units. Say, use this slider, and yeah, obviously that it should be the negative side. And now we're all set. Should go over here. It's the same. Let's look at the pulled curves, so they will come along. Okay, now I will organize this nodes and components, more over here, and yeah, add to the group. We need to replace these existing points with the pulled ones. Even 2. For that we will use basically a list structure, so it's called replace. Yeah. So we go to, I will It's more closer, yeah. So you go basically in this tree, lists. We would like to modify this list. So we will replace the pulled items. Check the data structure of the pulled items, and you see that again we have a tree structure. We can check it with the panel and see. And yeah, so each item are wrapped in a list, and then we need to flatten. And then define this. This is the items that we would like to replace with. And now we need to give the index for each item that we want to replace, which is actually here given. The index values for that closest points. And again, this is a list of things that are in a data structure, data tree structure. So we need to flatten that as well. And then we see that the index values, if we hover over the I output here, that we see the index values are written. And then we plug this into here, and then we just see the result that we now replaced that items, that point items here with the ones that we pulled actually. And then this is the point cloud that we now would like to create a surface out of this point cloud. We write surface from points. Yeah, this should be the component. Surface from points. Let's give our set of points. And then this is the U count, the number of points in U direction. We can basically use the same U parameter which is written here. Use the information from the first point list. Let's go over here. Let's check it out, the list length. And here, just by plugging this into that, and then you see 11 locally defined values, it's written. And then I can just basically take this number U and then use it over here. And you see our surface is created. This is deformed surface. Let's check. Yeah, if by basically moving this plane, sorry, moving this curve. Yeah, but we can change. We can define more deformation. Yeah, exactly. So whichever you like. Yeah, you can just define your modifications by changing these parameters. So in order to have it as a sitting element, that probably we need to pull more. that seems okay. Yeah, you can do more precise calculations, obviously, but for the sake of using our time wisely, we can just move on and then create waffle ribs based on this morphed surface.